Hello, in this video we're going to look at linear systems and matrices. So let's begin with the definition. A linear system is a collection of two or more linear equations. So I'm going to give you an example of something that's not a linear system, and then we'll go ahead and look at examples of linear systems. So here's an example. Let's look at y equals x squared together with y equals 2x plus 1. This is not an example of a linear system. And the reason that this is not an example of a linear system is that we have an x squared in here. So to be a linear system, all of the variables need to have an exponent of 1 or less. Okay, so that's not a linear system. In our class, we will be looking at linear systems. So let's take a look at 3 different examples now. Get that positioned. In our first example, let's solve the system. We've got x plus y equals 5 and 2x minus y equals 4. And when they say solve the system, they want us to find x and y that satisfy both equations. And if we had more equations, we'd have to satisfy all of the equations that were given. All right, so let's look at a visualization of this problem. If we look at the graph of x plus y equals 5, that looks something like this line. And then if we plot 2x minus y equals 4, that looks something like the following, roughly speaking. And so from our drawing, it looks like there is a solution. It looks like there is a point where the two curves intersect, and this is our intersection point. And our goal is to figure out what the coordinates of that intersection point are. All right, so let's work on our solution. To solve this, we're going to use a technique called elimination. And our goal is going to be to eliminate that y variable. So we've got an x plus y equals 5, and we have a 2x minus y equals 4. And if we just add up those two equations, what we get is we get a 3x, the y's cancel, equals 9. In other words, x equals 3. And from this, we can substitute x equals 3 into either equation. I like the first one, so let's plug it in there. We've got an x plus y equals 5, so plugging in a 3, we have a 3 plus y equals 5. Final answer there, y equals 2. Okay, so our solution here is xy equals the point over 3 up 2. Okay, so there's our answer, and we could label this on our graph, 3, 2. The point is we get a unique solution. We found a solution, and there's actually only one solution. So this case, I'm going to label it unique solution. There are no other solutions to this system. There's a one and only solution. Great. Let's take a look at another example. So this is example 2. In example 2, we have two equations here. Let's start off by plotting these, and we won't always be able to do this. Imagine if we had 100 equations and 100 variables. That would be pretty complicated, but to start off in our course, we want to get an intuitive feel of the different cases we might encounter, and so I think it's helpful to keep our examples small. Our other graph would look like the following. Oops, get rid of that. And this line is negative 4x plus 2y equals 2. And we notice that these two lines are parallel. And so in this case, there is no intersection point. And so if we're looking for solutions of the system, we're looking for x, y values that satisfy both equations, it looks like we're not going to get an answer. It looks like there's going to be no solution to this system. But let's see what happens if we work through this algebraically. So here's our solution. For this technique, let's use something called substitution. And you can use a variety of different methods, but just want to demonstrate substitution here. So let's first solve equation 1 for y. So let's label this equation 1. And let's label this equation 2. Okay, so let's solve equation 1 for y, and if we do that, we get y equals 2x plus 3. And now let's substitute that. We'll substitute equation 1 into equation 2. So let's do that. Equation 2 says negative 4x plus 2 times y equals 2. And we know what is y. We just solve for that. That's 2x plus 3 that we found up here above. All right, so let's work this through. We get a negative 4x plus 4x plus 6 equals 2. Those 4x's cancel out, and we end up with something that says 6 equals 2. And we know that's not true. 6 is not equal to 2. Since we got a situation that's impossible or something that's never true, this tells us that there is no solution to this system. So this is another type of outcome you can see. In the first example, we saw a unique solution up above. We go back to that one. Here we see an example of no solution. Let's look at one third and last example here. This says solve the system. Again, I'll start off by plotting these lines in the xy plane. And if we do that, we get something that looks like the following. We get 4x, oops, that moved on us, so let's move that. 4x minus 2y equals 6. And if we plot the other line, it turns out that they're collinear. Both lines lie right on top of each other. So this is our 6x minus 3y equals 9. And so in this scenario, it looks like there are infinitely many intersection points. And so we might intuitively think that there are going to be infinitely many solutions to this system of equations. Okay, so let's go ahead and solve this algebraically. So solution. In this case, I am going to try to eliminate a variable. So let's try to eliminate x. That's going to be our goal. For the first equation here, I'm going to multiply that by a negative 3. So let's do that. We'll go negative 3 times our first equation, which was 4x minus 2y equals 6. And for the second equation, let's multiply that one by a 2. And the reason for doing that is that this will allow us to cancel out our x's. Okay, so if we look at what this gives us, we're going to do some distribution here, right? Distribute, distribute. And so what we get here is we get a new system of equations. So let's write that down here. We get a negative 12x plus 6y equals negative 18 for our first equation. And then the second equation, similarly, we distribute through. We get a 12x minus 6y equals 18. And we add those up. Everything cancels. In other words, we get 0 plus 0 equals 0. This equation is always true. And this is what tells us that there are infinitely many solutions. Any x, y points that live on the purple line, the 4x minus 2y equals 6, they also live on the other line, the red line. Infinitely many solutions here. Okay, so I'd like to pose a question for us to think about, and let me just move this up a bit here. So the question that I'd like to think about is, given a linear system in two unknowns, for example, x and y, we've already seen that we can get a unique solution, no solution, or infinitely many solutions. And the question is, are there other possibilities that exist? Could we ever get two solutions, for example? So I'd like to explore that a bit. Let's suppose we have three lines in the plane. So here's a line, here's another line, and here's another one. So we've got three lines, so it's certainly possible that we have three equations and two unknowns. We could get a unique solution. So that's fine. We also can get our no solution scenario. So that would just be like three parallel lines. So that works out. Doesn't matter that we just had more equations. We can still get no solution. And certainly we could get infinitely many solutions. So we could have all these lines lying on top of each other. We could have these lines being collinear. Right, all lying right on top of each other, and this is our infinitely many solutions case. And the question is, are there other possibilities? Well, one possibility that you might be thinking of, would be something like this. Suppose we have two lines which are parallel, so they don't intersect, but then we have a third line that intersects each of those. So we've got a transversal. And the question here is, how many solutions are there to this system? Well, the answer is there are no solutions. And the reason that there are no solutions here, because a solution to a system has to satisfy all equations. And this point up here only satisfies two equations, and similarly this intersection at the bottom, that only satisfies two. We don't have any points that satisfy all three. So that's no solution. So it is true, we only get three outcomes for linear systems. So we get unique solution, no solution, infinitely many, even if we start putting in more lines. All right, let's crank it up a notch and consider linear systems which have more variables. I'm just going to zoom this out a little bit, fit it on our screen. So given a linear system of three equations and three unknowns, for example, x, y, and z, what types of solutions exist? So in this scenario, we're looking at things like ax plus bx. That should be a y, so let's actually erase that. by plus cz equals d. This is the general equation of a plane, and so when we try to visualize a plane we're drawing on our paper, we draw a perspective drawing. And so I'm going to let x be the axis that points directly out of the page towards you. Y will go left and right horizontally, and our z-axis will go up and down. So these axes actually continue, and this x continues back into the page. Now to draw a plane would look something like, a post-it with a pencil through it, right? So if you try to draw a little plane up here, and then I'll darken in our z-axis. So there's a plane, okay, and it goes on infinitely long and wide in all the directions. All right, so there's a plane. Now, the question is, let's consider three different planes and see what happens, will we get no solution, unique solution, and things like that. So scroll this up a little bit. So let's consider kind of three planes here. I'm going to draw. So there's one plane. Let's draw another plane here that's parallel, so to speak. And then we could draw a third plane. And then I'll put the axes right down through the middle of these. So there's our y-axis, our z-axis, and our x-axis coming right out towards you, and of course into the page as well, if I wanted to continue those axes. But here's a case where we have no solutions. So we have a system of equations in 3 variables. We have 3 different equations represented by these 3 different planes, and they don't intersect, so there's no solution here. Okay, let's look at another example. So here's another way in which you could have no solution. So you could have 2 planes which are parallel. Okay, 2 planes which are parallel. And then we could have a third plane which cuts down and intersects those other 2. It slices right through. And again, no solution here. The reason why there's no solution is because, there are points where the turquoise plane intersects the purple one, and similarly turquoise with the green, but there are no points that intersect all 3 planes, so that's why there's no solution here. Now we could also have situations where we have a unique solution, so let's draw a plane in the plane of the paper. We'll also draw another plane that kind of lies maybe as a floor coming right out of the page at you. So I'll kind of draw that there, and it goes back behind this purple plane. And then let's draw a third plane which is perpendicular to each of those, or orthogonal to each of those. And that'll be kind of like a wall here. If you imagine this is like a perspective drawing of a room, and that goes down behind. This has a unique solution. So the place where all 3 planes intersect is right there. There is our unique solution. This is the intersection point. Okay, so the solution is a point there. Other situations that could arise, we could have infinitely many solutions. So one way of visualizing that would be to think about a plane. In fact, we could put all planes together. They could all lie right on top of each other. This is all planes are coplanar, we could say. There's the turquoise one. And this is a case where we get infinitely many solutions. We can also get infinitely many solutions in another manner. So let's compare these 2 examples. So here's a different scenario where we've got 2 planes that are coplanar. So we'll put the purple one and the green one together. And then this third plane cuts down through, slices down through that plane. And in this case, the intersection is that line right there. Okay. So again, we get infinitely many solutions all lying on that line, but the solution space is a line. And lines are one-dimensional creatures. Over here, our solution space, I'll write that out, solution space is a plane. And planes are 2D creatures. So our solution space was actually all the points here in this plane. Kind of look ugly if I color it all in, but you get the idea. So we get different sorts of solutions. We can get points, which are zero-dimensional. We can get planes, which are 2D. We can get lines, and we can get many other things. But the big picture idea here is that we only get 3 possible outcomes. So for a linear system, we get either a no solution, a unique solution, or infinitely many. And it really doesn't matter how many dimensions you're in, whether you're talking about lines in the plane or planes in 3D space. So let's summarize that right now. So our summary: a linear system has either a unique solution, no solutions, or infinitely many solutions.